Thank you very much for having me as a member of Advancing Preconstruction presenters. I'm Tsukasa Ishizawa from Takenaka Corporation, one of the top 5 general contractors in Japan. My topic is titled as Understanding the Implication of Computational and Generative Processes on the Design Workflow. So today, I'd like to talk about the computational design, especially from the Japanese general contractor's point of view. First of all, let me introduce about Takenaka Corporation itself. Takenaka is one of the largest general contractors in Japan. We have more than 13,000 staffs internationally, and among them, 2,400 of staffs are licensed architects who majorly belongs to the design department. The corporate history began at the year of 1610 as a group of carpenters. Since Takenaka transformed into a modern corporate at 1899, we have completed numbers of landmark projects locally and globally. Here's 3 major keywords to understand the spirit of Japanese design and build project scheme. A man at the center of this ancient picture was called as Torio, a master builder leading a group of the craftsperson. Torio was expected to have 5 different skills in one personality, which was building design, estimation, carpentry work, drawing, and detailing. So in Japan, it was widely accepted for long that one single entity undertakes both design and construction service together, which was possible by the high trust due to quality from the client. Although we are involved in the multiple project scheme today, the ratio of the design-build project occupies at around 60 to 70% of the total project every year. As a one-stop service provider, Takenaka has more than 1,100 staffs under design department. In addition to the 450 numbers of the in-house architects, we have more than 200 structural engineers and MEP engineers who can participate to the project from the beginning. That enables the early staffing of the engineers and construction planners from the beginning is the early stage of the design in every design and build project. By the effect of their early involvement and the total elimination of bidding process enables to shorten the project delivery. Having said that, it allows to postpone the design decision making until the part really comes to the production stage. As such, the construction detailing and approval usually happens after the construction started with the official involvement of the project architects. This is the visual analytics of the corporate project database. Based on the experience of thousands of completed projects in Japan, Takenaka has actively received numbers of projects since the 1970s in Southeast Asia, Central Eastern Europe, and United States. Takenaka is concentrating to the middle to large-scale building projects. Here's another look at the corporate project database. The plots are of the project gross floor area per building types. The median of the floor is at around 3,000, but the average lie at 7 to 10,000. Not only the landmark project in Japan, cities such as Tokyo Tower and Abe no Haruka's, the tallest building in Japan at the moment, Takenaka was the first one who realized the first unitized building project at Antarctic Expedition Base at 1955, and the first air-supported stadium in 1988. Takenaka completed 15 airport projects so far, including Changi Airport Terminal 4 in Singapore. We are also involved in traditional and historical building projects too. The images on the right bottom is the one from the Nagoya Castle, which is under the design stage to be completed on 2022. Talking a bit about myself, I entered to Takenaka on 2006. Here's a photo when I was at the construction site as a junior site manager. Most of the time in Takenaka for 15 years, I was a project design architect. I have completed multiple commercial, residential, and industrial projects mainly in Tokyo Central Business District. Also, I spent my 4 years in Singapore as a project BIM manager from 2012. Here's 2 major projects I was involved in, and I completed the construction BIM model by the collaboration with the BIM team and tens of BIM subcontractors. So today, I'd like to cover these 3 major topics corresponding to the original agenda. In the part 1, I will introduce my Singapore project to talk about the generative design approach to enhance the productivity in the production and construction stage. Part 2 is more for the design stage. I will introduce a couple of projects to think about how we can actually conclude design after using algorithms to generate numbers of design options. Part 3 is to leverage the computational approach in the broader aspect. Unlike the earlier project-specific examples, here I will present several scripts to resolve the common problems among the projects. So let's start from the part 1. The project is called as Capita Green, named after the project client, one of the largest developers in Singapore, CapitaLand. As the name offers, the project is characterized by the greenery around the facade and the rooftop, and much more than that, the huge rooftop structure installed at 200 meters high from the ground. The project architect Toyo Ito, the Pritzker Award winner of 2013, wished to realize a building that is like a plant growing toward the sky. That is the reason why the building envelope is double-skinned with installing the plants in between, and it has a flower-like structure on top to allow the natural ventilation for the entire building. This is a completed building located at the edge of Central Business District in Singapore. And here are some more views of the building features. You can find 2 different types of double-skin facade with plenty green. Here is an aerial view looking down at the building top wind catcher and the rooftop forest. Here's an infinity swimming pool on the 38th floor. And this is a night view from the different angle. The wind catcher was planned to contribute to the energy reduction. 2 big leaves, like petals of the flower, are facing to north and south to capture the prevailing wind, which is almost stable in the tropical climate throughout the year. The cool and clean air is then distributed to the office floors of the building throughout the concrete duct penetrating the building from top to bottom. It simply meant that this structure, which actually has 45 meters high from the building top, needed to stand with the wind at all times with the cantilever from the bottom, with keeping the enough opening to allow the sufficient ventilation for the habitable area. I still remember the first word I saw when I joined the project. I was so curious about how the structure was planned in the schematic design phase. The statement I witnessed on the tender drawing was, "The structure and finishing to be confirmed." Unbelievably, our company applied to the design bid tender and somewhat quoted this huge thing and pricing without details, and eventually we won the project. I took the Rhino model and started to analyze the geometry. Here's a view on the analysis. Though initially the geometry seems to follow some simple rules, but actually it totally wasn't. I anticipated that this is because of the long-term design study and numbers of modifications made on the original intention. I admit which often happens in the design stage, so I needed to discover the underlying principles to compose this shape before I proceed to the detailed design phase. Lucky enough, I could discover a good approximate. Sphere didn't fit the provided curve, but the torus fit very close. If we know the geometry follows the torus, then it assures that the form is symmetry and the short section always follow the same curvature. We thought it provides numbers of benefit in the later stage because if we modularize the shape appropriately, then the cross joints of the elements can be standardized. The table on the right shows the radius of base geometry in colors. So far, we have reduced the number of curvature types down to 10. But the larger question was how actually we can compose the structure inside. It seems that the steel framing was the only way to make this 45-meter high structure happen. But there may be multiple ways for the framing, like lattice, truss, or diagonal grids. To select the best composition, we first generated 36 different patterns to calculate the total steel weight to find the minimum. Also, we tried to minimize the expected welding length, as this structure is at the outdoor, and welding work is expected to carry out during the rainy season. At the same time, we also evaluated the distance of double-side cladding, because minimizing this parameter would make the design closer to the original intention. Here's an overview of the simulation. The comparison is here. The green bars show the total steel tonnage, and red line is for the accumulated welding length. The case 2 showed the minimum steel used as a structure, but finally we adopted case 1, since the welding length was minimum, and the simplicity of the structure seems to be good for the production. But this was not the end. We needed to design the substructure to withstand the wind load at the 245 meter high from the ground. The good thing was that the curvature was fixed in advance. We could standardize the detail for most cases, but in reality, the modeling work in Tekla took huge time to complete, and moreover, some engineer and the site manager found it difficult to work on the 3D model, mainly because they are not very familiar with the model navigation, and they couldn't convince themselves enough to judge on the model. I talked to the modelers in Japan to quote how much will it be to create a physical model of the structure. What I understood was purchasing the 3D printer was 10 times cheaper than the conventional model making. Assembling the 3D printer itself took whole 2 days, so the printed model helped everybody to understand and communicate about how they approach to the problem. Finally, we created a model for the scaffolding for the construction team to study how they need to treat the penetration of the supporting to the finishing. This also helped to minimize the scaffolding materials that was essential for the construction planning to eliminate the unnecessary hoisting up to the building top. The finishing details are developed accordingly, and we finally moved to the installation stage. But that was the time I realized my mistake in the model. The finishing was still represented by simple rhino surface, and I was sure that the substructures are aligned with the surface at all time, but it wasn't. It was obvious when you cut a section, you can see quite a gap between the T-section and the surface. I got a call from the factory that the screw doesn't work to fix the metal sheet. Eventually, I needed to install the steel pieces to allow the screw work, which was very time-consuming task for the steel fabricator. Although the additional cost was absorbable by the saving we made so far, but this is my precious experience to realize that the Rhino or Revit model is nothing more than one type of representation, and you have to use multiple ways to fully understand and verify if the design strategy is really viable for the construction stage. Moving on to the part 2, I'd like to focus on the computational design on the early stage with the consideration to its subsequent detailing and construction phase. This is another project example of the parking building located in Tokyo, which was my first building completed as a project architect. The building was almost completely for the parking except for the shop front at the ground and first level. The building was a part of regional redevelopment, and the parking facade is to face to the train station. The client was a department store. They wished to have some expressive facade to welcome the people to the commercial space. The requirement was to cover the entire building but keeping the opening for natural ventilation with the material at very high cost performance. I mean, it has to be very cheap. I took a motif of flower from the department store logo and converted it to the pattern for the building envelope. The facade material is a cast aluminum frame with reliefs to give some patterns. The frame is basically open so that we could provide a sufficient opening for the required ventilation. As the pattern goes for thousands of square meters, I try to create something that does not easily repeat and to give some festive impression for the customers. Actually, the pattern was made only by 3 types of the panel shown in this diagram in A, B, and C. The panel units are in the same size. I designed 3 different reliefs arrangement and carefully laid out to represent the randomness, but it can be quite simply represented in the drawing. The computational design approach was effective to generate many different answers to choose the one from the design point of view. Here's a detailed drawing for the panelized facade, including the irregular panels at the corner and the side of the building. The total randomness was fully controlled by the arrangement of 3 variations of each panel layout. The reason why I limited the number of variations was because of the production phases. The facade panel was produced in China back to 2008, right after the Olympic Games in Beijing. Although we have checked multiple ways to production, this sand cast and welding method was the most cost-effective at that time. The pieces of flowers motif are casted and welded together to make a bigger panel. To eliminate human error in production, the factory needs to prepare the jigs to lay out the pieces correctly, and these jigs are often expensive. So minimizing the panel patterns reduces the number of jigs, simplify the production lines, and rationalize the total price for this part. As Grasshopper was not widely used at that time in 2008, I created a Pascal-based script in Vectorworks to generate the patterns. Starting from the completely random pattern for whole building facade, gradually I modified the script to find a good division for the panelization and limiting the number of the types by trial and testing different arrangement in each unit to see the overall effect of the facade design. As a code requirement is clear from the beginning, the study was all about the best design impression with the minimum impact on the production stage. It greatly facilitated the conversation with the subcontractor because it looked complicated, but the things they need to take care was already streamlined. Here's one of my projects most recently completed. The building is a head office for a logistics company located in Tokyo, and the building is required to achieve at least 35% energy saving to rationalize the building life cycle cost. These perforated panels are outer skin of the building to work as a shading device to control the sunlight intake to the interior workspace. This is the internal view looking at the facade. The building has 2 types of the facade, and in this case, one type just had a grid opening, but in the other one shown on the right side in photo and bottom in diagram, the square holes are inclined to control the sunlight. As you can see, the left panels in front of the courtyard allows the sunlight coming in, but the right ones at the workspace cut out the direct sun. The inclined holes are designed to shut the direct sunlight throughout the year to reduce the solar radiation, especially for the summer season, to reduce the HVAC energy consumption, and to maximize the comfort time at the spring and autumn season. Controlling the direct sunlight also effectively suppresses the glare for the working environment. The whole angle and panel color was set to diffuse the light to give the indirect sunlight, which is expected to contribute as the natural lighting source. At the same time, I needed to prove that the facade gives some sense of openness for the office users. Otherwise, the working people may feel suppressed without having any feeling of the outdoor. Lastly, the facade panel needed to be open to allow the natural ventilation to further reduce the HVAC energy. As the building was facing to southwest, designing the shading to cut the incoming sunlight was not impossible for most of the time throughout the year. But obviously, 100% shading is very difficult because closing against the ray around the sunset will result in almost complete close. Then it may be nothing different from just a solid wall. So I needed to balance among three different criteria: the shading performance, and the lighting effect, and the sense of openings. The shading performance can be tested by giving the sun ray for every hour throughout the year. We ran the batch to calculate the ratio of sunlight penetration and visualizing the heat map. But actually, this heat map is just an Excel spreadsheet colored by the calculated number. The green is for the 100% shading, and the more color gets red, the more sunlight will come in. So by looking at the green part of the chart, we can visually understand how the facade configuration works good as a shading device. This is another look at the facade by radiance to understand how the visual comfort at the workspace will be affected by the panel holes. The rendered image are to visually understand how much lighting will be gained from the direct and diffuse sunlight. The illuminance simulation is to take care of the glare. We evaluated the risk of glares by the contrast between the brightest part of the vision and the average illuminance. But more intuitively, we just needed to eliminate or minimize the yellow part in the heat map so that the glare will happen less often. The last one is for the openness. This seemed quite subjective issue, but we found scientific papers that address to that issue. These are the theories to evaluate the sense of opening by applying some calibration to the viewer's vision. Fortunately, the formula was not very complicated. We implemented this logic into the evaluation and created another heat map to visualize how the office users will feel when they look at the facade from inside, from the sampled points on the floor. The green shows the part where they have better feeling for the openness, and red is opposite. So here again, we try to get rid of red parts by controlling the panel configuration. In fact, these three simulations examine different objects. The first one is for the facade panel itself. The second one is for the indoor lighting environment, and the last one is for the sampled points at the floor. So the point was how we conclude, because very often the synthesis of the simulation will fall to Pareto optimality, where the parameters are in trade-off and it gets too difficult to select one from the numbers of answers equally good. Rather, we created this holistic view on this simulation to visually judge what has to be improved. After multiple improvements in the dimensions, we could reach the conclusion at the 7th round, where all three aspects drastically improved from the first design iteration. This was a time when we started talking to the subcontractors, and it facilitated us to prioritize which dimension to be kept, because we have already learned which part is the most effective part to enhance the result by the past iterations. Again, we didn't forget to create a simple mockup to verify if what we aimed was actually achieved by the design modification. This was just a cardboard mockup in white, but it was sufficient enough to convince ourselves that the design judgment is in the right direction. We thought the same approach was effective in dialogue with the client. So not only taking a piece of model to say like, imagine that this setting repeats for whole building facade and it's exactly what we want to do, we presented the 360 rendering view with a VR device to show how it's effective, how it will be effective. We found this was a good approach because the immersive experience is sometimes difficult to share among the stakeholders, but it can be aligned by talking on the physical model. So here again, the combination of the different representation gives multiple views on the issue and often helps us to understand the nutshell of the problem swiftly. So far, I was talking about the project-specific examples where the programming person is on board. But honestly speaking, such computational design enabler is in short, and we need to think about how we can approach to the broader population to leverage this sort of approach. The company launched a new group named Computational Design Group, which was made to do the project consultation, the tool development, and the information sharing with more than 1,000 in-house of architect people. Although the team is quite small at the moment, different skill set and tool set are flexibly configured per project and problem to resolve the issues on time. Some problem is commonly found in specific project sites. C-value is a criteria to evaluate the visual comfort. It simply measures the distance between the view to the specific point of focus and the obstacle, mostly the audience in front. Usually, it's said that 60 mm is the borderline, and 90 mm is good, and 120 is reaching the view. Obviously, this influences to the section design, and better C-value is in trade-off with the step-rises dimension and the building volume, that's the structure cost. So finding the appropriate C-value is crucial at the very beginning stage of some project. As the C-value calculation is mathematically simple, the implementation is not very difficult, though the script looked a little bit complicated. After creating an engine for C-value calculator, it can be used for the theater and auditorium project to generate the building section by the fixed C-value, or to evaluate the visual comfort for the provided design and the seat arrangement. Sometimes it's useful to limit the extent of view if possible, because it allows to provide more seats in the same space and it will enhance the ticket sales. Interestingly, this was applied to the aquarium project, where the client wished to design the largest dolphin show pool in Japan, with ensuring the satisfactory experience to the watchers. Taking this C-value engine as its part, we also developed a standard program to generate a football stadium from scratch. Here we needed to incorporate the evaluation for the evacuation time for the emergency case and the exporting function to the structural calculation program to streamline the design stage from the beginning. The most crucial part of the stadium basic design is to ensure the required number of the seats, but the count of seat numbers hinders the flexible design study. This program automatically generates the stadium volume by inputting the field size and some basic parameters. The program also allows the occlusion object to omit some part of the seat from the count. The stairway and aisles are also automatically generated by the given numbers under the maximum allowed number by the building code. After arranging the vomitory all around, then we can draw a path for the evacuation from the seat to the corridor. And by multiplying the moving speed and some other bottleneck factors, we can get the time until all the audience move out from the stand. The calculation is regulated by the Japanese building code, And here is a network diagram created accordingly. In the open roof stadium, the primary evacuation has to be completed within 8 minutes, which is crucial for the building design, but very often it was verified only after the schematic design solidified. This calculation is completed within seconds, so the architects can start exploring the design without going far beyond the acceptable range. For the general contractors, the most significant benefit of this is to suppress the changing factor in the design and to assure the estimated project cost from the very early stage. The neural network is applicable to the design study too. Once we can prepare the sufficient amount of teaching data, the neural network gives us swift outputs, which greatly help architects to base on. As the nature of the learning process, it never becomes error-free. It absolutely contains some part that human architects need to interpret appropriately. But it has a huge potential to assist the architects to make better judgment in many aspects. GAN is a type of neural network, which is an acronym for the Generative Adversarial Networks. Two different neural networks compete each other and rapidly learns to generate the visually satisfactory outputs. This is often used to colorize the monochrome photos and to generate the photorealistic images from the sketches. We try to create an automatic generator of the sprinkler system based on the architectural plan as input. We took drawings from the past completed project and applied the color codes to enhance the learning processes. The green lights show the piping and the sprinkler heads in the images, and the left one is the output from the system, and the right side is the supervising layout. The system doesn't work good from the beginning. You can see the blank at the building perimeters, perhaps because there is no sufficient input for the system to base on. But after several rounds of tunings, the neural network learns to populate a better output, in this case, the more reasonable output from the engineering perspective. The point is that the system doesn't know at all about the building code and engineering requirement, but it only tries to create something similar to the supervising dataset. Although it still requires improvement in some area, but this means that we can generate a rough idea of the sprinkler system with spending almost no cost based on our past project experience. And the system potentially grows further once we input more project data from the teaching dataset. The detail of this project is available in the conference paper on ICADE 2020. Please go to the site at Kumincad and find it by my name for your further reference. This is another example of machine learning-based system for the wind simulation. CFD simulation takes hours to obtain a result, so examining the building volume options can take up to several days to complete. This simulation is again the neural network basis, and the heat map is made without actually running the CFD, but learning from the past CFD teaching data. The accuracy we measured here is more than 95%. So it would be good enough for the basic design phase to determine the massing strategy. As you can see, the system responds to the rotation of the building volume within tens of seconds. So testing hundreds of massing options is becoming feasible. Lastly, I'd like to introduce a small example about the interface. This is a project I supported to generate a facade pattern. And in this case, the design criteria was not very clear, and I was asked to create a program to explore the numbers of different facade design, but without manipulating tens of slides. It's reasonable because the designers themselves also wouldn't know how the building would be like at the very beginning stage. But somewhat, the system needs a loop of input and feedbacks so that the architects can narrow down the possible design options. I came up with the parameter control and the sound effectors for the electric guitar. The sound of guitar is made by the combination of effectors like overdrive, equalizer, harmonizer, and so on. And the player simply control knobs to get the desired effect. Mostly the player do not imagine how the circuit works inside, but intuitively turn the knobs to make the sound image closer, or sometimes inspired by the obtained result. I knew that the project architect plays the guitar, so I tried to give the program interface just like this, with completely hiding the inside of the box. So this is the deliverable, and you can see two panels roughly mimicking the guitar effectors. Two panels on top generate the patterns of the panels, and knobs on bottoms are to control the greeneries with adding some randomness. Figures displayed actually represent some factors, but most importantly, this interface shortlisted the parameters to manipulate and set the range to control within. The clarifying the entry point to the tones of design generation is important to get a broader audience in architects who are fully responsible for overall building aesthetics and functionality. Here's my concept for the computational design and data-driven architectural design. What matters are the combination of these three: data or the model, database to derive the trustworthy information from, and the analytics method to obtain the useful insight which leads to the better solution in the project. With combining a due consideration to the security issue, then the implementation is almost ready. But what's more important is the people who actually use it, study with it, and take the result to the project stakeholders. Training everybody to become data savvy seems ideal, but actually impossible because the architecture itself requires a rigorous skill set, and it's getting harder and harder to master. So rather than normalizing the basic skill for everybody, the point is to decompose the problem, resolve the issues with using the standardized approach whenever possible. Sometimes I'm asked if the artificial intelligence can create a whole building or even city itself. From my project experience, it sounds very difficult because the synthesis of individual attempts is way beyond the simple optimization. It contains numbers of logical leaps, but that makes an architecture as an architecture. The architects should work sometimes as sensors to perceive the real world, sometimes to come up with alternatives to the simulated result, or often to create a wisdom from just a set of information or piece of knowledge. Then the individual attempts and the computational design seems to remain individuals, and it will be maybe partially true. Christopher Nossel writes about the concept of agentive technology. The agents are so-called weak AI that intelligently works, but in the limited field, like the recommendation in Apple Music or Amazon. This is actually where the AI solution gradually replaces to the human decision making. This he states in the book as your mission should you choose to accept it. So the generative design and the computational design or its approach is powerful today to generate the alternative solution which contributes for the effective design process. But in the long run, by accumulating the components, the individual solution gets smarter and it will carry out the work in some specific fields. That's when the people put their trust on the agent and try to make the decision at the higher level from more holistic view. That will become the future competency that has to be strengthened by the collaboration with the computational technology. Thank you very much for your attention. I'm sorry that I won't be able to answer to the question at the moment, but your questions, comments, and opinion for today's presentation really welcome. Please contact me from the email, Twitter, LinkedIn, or whatever possible. I hope you enjoy the rest of the program and have a great day ahead. Thank you.